between the depth, right? So on the left one, I'm just projecting it on a flat wall and looking at it, and on the right, that's the offset that comes from the book, right? And by the way, what is this little pattern, this little thing here? That's a shadow, right? Because the thing is offset a little bit, and I'm projecting here, there's a little area right here that I can see with the camera that can't be seen by the projector. That's what the black pattern is. In this particular case, the projection is coming from this side, and the camera is coming from that side. All right. So if you actually wanted to build this, you have to implement an algorithm for doing it. Now I'm going to tell you, I took this algorithm from, I think, Derek Hoyam's slides. They're on the web that he took from somewhere else. So I don't know for sure that this algorithm is the one they use, but it sounds pretty good. All right, it's similar to what you would do. So first thing you do is you project out these dots, and you just detect them. So you detect these speckles, and you label all of them as unknown. I don't know their depth. Now what you start doing is you randomly select a dot that's labeled as unknown. And then you take this windowed search, all right, doing a normalized correlation, and along a scan line, that is, I really should say along an epipolar line. I know exactly where to look, okay? And I check for the best match. And by the way, I have to make sure that that best match is good enough. If that best match is not so good, I mark that dot as invalid, and I start looking for new dots again. But if my first match is really good, I start doing what's called region growing. I start looking around that neighborhood for matching other points against the known pattern. Okay? Oh yeah, by the way, what am I correlating? I know the pattern I'm projecting. So I've got my little local pattern of what's called pseudo-random speckle points, and I just correlate them around. And so pixels nearby are added to a queue. For each pixel, I initialize its offset, looking for it from the one I just had. I search around a little bit, see if I find a good enough match. If so, I label it as matched with its offset, its disparity, and then I look for its neighbors and I add them to the queue. And I stop doing that when that queue is empty because I finished using this anchor point, and I go back again and I reinitialize, I pick another point, and I stop when all the points are labeled as with a known depth or marked as invalid. So what makes that work is that I have this pseudo-random pattern, so any little patch can't be matched everywhere, but is matched sort of just in one place well along that epipolar line. I know those patterns, and so I can just drive that search very quickly. There's a cool little video on YouTube. Let me just show that now, and it explains how this works. I'm actually going to cut out the section when it starts talking about rabbits, but that's because you guys already understand how stereo works.
Microsoft's Kinect has a depth sensor that can tell how far away things are. In this stream, brighter colors are closer, and darker ones are farther away. This video will explain how it does this, which is pretty clever, and not how many people initially thought it worked.
By the way, these things are relatively easy to implement. You could implement these things too. Just hook up your Kinect. You can just write a little program, or even in MATLAB, you can do it directly and display it, and it's kind of cool to experiment with. The thing that I like about this video that you can see well is he sets it up so you can look at this in a dark room using a IR sensitive camera, which, by the way, most digital cameras are IR sensitive. So if you do this, you can probably look at this on the video feed coming off of your digital camera while you've illuminated things with the Kinect, and you'll see it.
Now if you take a night vision camera and look at the projection from the Kinect, you won't see a grid of numbers, but rather a random speckle pattern. This accomplishes the same goal though, because no group of specks looks like any other, so the Kinect automatically knows the angle of every group, and can therefore triangulate distances, just like shown before. The downside of this technology is that it can only work indoors because sunlight would wash out the speckle pattern, and similarly, multiple Kinects would confuse each other.
All right, so we've looked at projected IR versus natural light. What are the advantages of this projected light or projected IR? Well, yes, it works in low light. You're not counting on having external light. You're not counting on having texture that you can deal with, since I'm projecting this texture. And it's okay if I've got repeated things because it's not actually repeated in the speckle pattern. Remember, we had this problem with picket fences in stereo of all the pickets look alike. To know which picket it is a challenge. Well, if you painted all the pickets different colors or different speckles, that's not a problem, and that's what the Kinect does. And in particular, you can tailor your algorithms to the actual pattern that you're producing and engineer the thing to work really well. What are the advantages of natural light? Well, it's natural light, so it works outdoors, it works in sunlight, it works, it just works whenever the lights are turned on. It doesn't work in the dark, that's okay, neither do I. But the idea is that, you're just basically using the scene. The other thing is you don't have to worry about the resolution of your projection. You've got your high resolution sensors. It's a lot easier to build high resolution sensors than high resolution projectors. Both of them have some difficulties. If you have very shiny surfaces, right, or specular surfaces like a mirror, right, so your projection is going to go. And, clearly, if I'm doing stereo and I'm a robot and I'm looking at a mirror, I see the thing that's up there, and I think, oh, I could just reach down here and get that light that's on this. Oh, no. Okay? It doesn't see the table. And my projector, well, it projects down, so it'll also be thinking about the ceiling. All right? So it doesn't work in either of those cases. Just want to end a little bit talking about, if you've got this way of recovering depth, how do you represent depth? That is, how do you think about the representation of it? We only actually talked about disparity. We talked a little bit about depth images, but not too much. But I want to talk about just two quick methods here. One is a depth image, and then there's a slightly more, I use the word nuanced, a little more recent notion of representing depth, namely point clouds. So depth images, as shown here, this was another one of those stereo figures from the Middlebury stereo data set, and this is a ground truth known depth image, right? So you see these rings here, right? Well, you see that this one's darker and brighter and brighter. They're at different depths. Likewise, this picture here is this picture there. It's brighter than this mannequin back there because it's closer. And if we had more grayscale resolution, you would see this would be darker than this area because the nose is further back from the cheek. So depth images have some nice representations. First of all, I've got depth everywhere, right? I can just go to every pixel and say, what's your depth? So I've got a full, dense depth representation. Something that's a little more subtle is that a depth image not only tells you it's 2 meters from here to that table, it also tells me that between here and that point is free space. So it doesn't just represent the surface, it also represents, by default, if you will, that there is no stuff between here and there. Right? So putting the point down there is also declaring that the ray from my eyeball to that point is free. So it's a representation both of the surface and of free space. People don't make nearly enough use of that fact, but it's true and important. The other thing is, often we need to think about depth discontinuities. Well, depth discontinuities are just edges in the depth image, and we have lots of processing for dealing with images. There are, of course, disadvantages. One is that it's very viewpoint dependent, right? I've got this scene geometry, but my depth image is based upon where my camera is. So if I move over here, I've got a different depth image, and combining them is difficult because they're in the reference frame of my image. They're not in sort of some natural reference frame that talks about the object. So it doesn't capture the geometry quite so much. And the other thing is, if I want to think about reasoning about the geometry, I kind of need to know where the camera is with respect to this in order for me to talk about where the geometry is. So what's a different representation? Well, a slightly more recent, newer approach is what's referred to as point clouds. And point clouds are essentially, you take all of your depth pixels that you hit, and you say, aha, that's a little, we used to use the word voxel, it's a little voxel of stuff, and I'm just going to hang it out there in space. And so I would get this constellation of points that's just a cloud. Okay, now I actually can't see inside surfaces, so it's maybe a cloud that I can only see the outside of, but if I had like another camera, and I knew how those cameras were related, I could take the points that it saw and stick them out in the same cloud area. And eventually I would have this big point cloud of depth points, and it would be a lot easier to reason about the geometry of those. Now, of course, when we do this, that point cloud sort of doesn't know how it got created, right? So did I look at it from here or did I look at it from there? So I don't have that free space information anymore. So point clouds, of course, have their advantages and disadvantages. The biggest one is probably that it's viewpoint independent, right? So because it's viewpoint independent, I can merge different point clouds as long as they're in the same coordinate system, and I can actually reason more about the geometry. The disadvantages include, so for example, it might not be very dense, right? In depth image, I've got a depth everywhere. Point clouds, whatever points I got. And if I want to know what's the depth going this way, I might not know the answer. I just know about these set of points. And so fundamentally, you've also lost this free space stuff, okay? Because you don't know so I have a point right here. I don't know if it was viewed from this way or from this way. If it was viewed this way, I know that all these pixels along this ray are free. From here, it's over there. I don't have that representation in point clouds. The other thing is, as I get further away, essentially my cloud, each individual pixel that I see is taking up a bigger and bigger voxel. So the point cloud density, the point cloud resolution, how big is a point cloud point? The resolution is determined by how far away from the depth sensor I observe that point. So nearby ones are tight little points. Further back, they're bigger voxels. But I didn't tell you yet about the biggest advantage. The biggest advantage about point clouds is the point cloud library. There's all this code out there, and it continues to grow, called PCL, for the manipulation of point clouds. And so that's code you don't have to write. All right, so it allows you to operate on depth, just not worrying about the details of the bookkeeping about these depth representations. So that's really a huge element. And one might even say if it wasn't for the PCL, the point cloud library, point clouds would not be nearly as popular as they are. Here's a pointer to what's the website? Pointclouds.org, all right, which tells you something, right? .org. This is open source, so it continues to grow and continues to improve. A couple other little things about point clouds. One is the point clouds, of course, are sampled from the surface that this depth sensor hits. So what you're getting is you're getting a sampling of the surfaces, which means there are no volumes. You have to infer a volume, right? So even if there's a nice sphere right here, you're going to get points along its surface. And maybe if you move around, you'll get more points from the surface, but it's up to further processing to decide, oh, that's this spherical volume. So there's no explicit representation of volumes. There is an interesting element to it, and that has to do with surface normals. So I assume you all know what a surface normal is. You've got geometry. So the idea is you've got some underlying surface, and at any given point, you could fit the tangent plane, and the normal to that plane, that's referred to as the surface normal. That you can think of as a first-order local approximation to the surface. Point clouds actually have surface normals. And you might ask, how is that possible?
How is that possible?
Well, because the sensor, it does a variety of little processing to try to find the little local points nearby and fit that tangent plane in order to estimate the surface normal. And sometimes that's useful. I will tell you that the surface normal representation is less robust than the actual location of the point itself. So this cute little needle diagram, in order to fit them, you have to essentially take a little Gaussian around the points that are there, fit a little tangent plane to those Gaussian weighted points, and then that gives you an estimate of the surface normal. You have to figure out how big a Gaussian do you want to use is a little bit like how big a Gaussian do we use when we take an image gradient. Remember that? We used to have to smooth out the image to get rid of the noise, but the more you smooth it, the more you've spread out the gradient. Same thing is true here. The more points you consider, the more smoothly the surface normal will vary. Suppose I've got a depth scene here, and I'd like to match it to some model or some previously observed depth scene. How might I do that? Well, what I need to do is I need to find some patches, some locations on my object, and match them to some locations on my object. And, it should be somewhat invariant to how I look at it, right? So I'm looking over here, looking over there, I want to find the same thing. The object might be rotated. We've seen this movie before. Remember we were matching pictures? We had two pictures that were rotated, translated, scaled, and we wanted to align them. Do you remember SIFT? SIFT was a way of saying, and Harris points, remember they were Harris-Stevens points and nobody ever remembered Stevens? We had ways of finding points and then generating a descriptor, and that descriptor had to be sort of discriminative and yet robust. That is, we wanted them to be relatively unique but robust, so that when we found a description here and we matched it with the description there, it would most likely be the right one. and then we improved that. We used ransack in order to find the right sets of matches. Well, we can do exactly the same thing with depth. You know, what's drawn here is that I've got this interest point, and I've got this sort of neighborhood of these 5 points around it, or I might look at